Alright, in this video I'm going to talk not about finding how a function changes, but rather how to find the function if somebody gives you what the rate of change is. So it's the inverse problem. Alright, now it seems a little odd. How would you know the change of something and you wanted to know the function? Well, actually that's more common than you think. For example, how about this problem? You have been driving for 3 hours at 65 miles per hour. Where are you? Okay, let's think about this question for a minute. So what is velocity if it's not change, right? So you have a velocity, and we can even plot that velocity. Let's do that right now. So and velocity is an example of rate of change. So velocity is the change in position over the change in time, and so it was 65 in units of miles per hour for 3 hours. So the graph looks like the following. Let's see, let's make it red. The red line for those 3 hours. Okay, now the question is, where are you? Okay, let's say that when we started, let's say the highway was, we'll pretend that the highway was on the x-axis. Okay, and so let's say we started at the 0, x equals 0, and we drove to the right, and so we need to figure out where in the world we are. Okay, how do we do that? Okay, well, let's look at the velocity. Look at what I said velocity was. Velocity is, by the way, velocity, you'll notice, is the slope. Okay, so you have this velocity graph. You've plotted the slope as a function of time, and we want to know where in the world we are. So let's just play with this graph for a minute. Okay, so let's cross multiply. So the delta f is equal to v delta t, right? We all know how to cross multiply. So if I wanted to know where I am, and by the way, for this problem, the variable is the position. So f corresponds to x. So if I want to know where I am after 3 hours, I do the velocity, which is 65, times the time that passed, which is 3 hours, and that's 180, 195. So that means that I'm going to be right over here at the 195. That's 195 miles away 3 hours later. See that? Okay. So what we just did was we found the f of x value given the slope, or the v of x, or the slope of x, whatever you want to call it. Okay, so this, can you see that this is the inverse problem? It's backwards to what we've been doing so far as we talk about change. Okay, so this is an important thing to be able to do, to find the f, the position, or the f of x in general, from the change, the rate of change function. Right? Let me bring something to your attention. Okay, you may not have thought of it this way, and it doesn't seem like there's much benefit, but later on we'll see why it matters. This is just giving you a taste of things to come. So the answer was that the position changed by 195. Okay, take a look at the velocity graph again. Okay, so what is the area of this yellow box? Well, we know how to do areas from geometry. It's length times width. So if you calculate that, you'd probably say, okay, let's see. So the height is 65, and the width is 3. Okay, so then 65 times 3, and that would give me the area. And so there you have it, 195. So notice a very curious thing. The area underneath the velocity graph is equal to the answer we were looking for, the position. Okay? That's, you wouldn't normally, you may not have thought of that, and it seems a little weird, but the point is you can calculate the value of a function from a certain area, from the rate of change graph. Okay? In fact, that is such an important idea that I'm going to write this right now. So you can calculate the value of a function from the area underneath the plot of the area underneath the slope plot. Let's say it that way. Okay? So in a weird sense, area and change are related. Okay, that's a big idea that's going to come up again and again. Okay, let's do a little bit more complicated example. Okay, let's do let's say a rocket that is, let's say, 100 miles from an asteroid starts firing. It moves, or a rocket that is 100 miles from an asteroid begins moving at, let's say, 200 miles per hour for 5 hours. How far is the rocket from the asteroid after those 5 hours? Okay, now why is this a little bit more... Oh, you know what? Actually, let's do this. Let's add another piece. What about if after 5 hours the rocket began moving at 100 miles per hour for 3 hours? So can you find out where it's going to be after that second phase? Okay, so two reasons that this is a little more complicated. We have two different speeds, and we also have an initial position that's not 0. It starts out 100 miles from the asteroid. So you could think of it like if we had an x-axis and the asteroid, let's say, is at the origin. Here's the asteroid. I don't know why it's blue, but let's just go with me. So here's 100, and that's where our rocket is at time 0 when we start our stopwatch. Okay, so let's see if we can handle this situation, and I will plot the velocity like I did before, and this time it's going to be 200 for 5, and then so let's see, we got to go to 8. So 1, 2, 3, 4, 5, 6, 7, 8, and it was going 200 miles per hour, and then it was going 100 miles per hour. And so I'm plotting here the velocity versus time. Okay, and so 200, let's switch colors. How about purple? And 200 for 5 hours, and then it went down to 100 for 3 hours. Okay, and by the way, in the real world, it's not possible to jump from one velocity to another one. You have to, it might not be a very long time, but you have to still go from 200 to 190, 180, and all the values in between. So I will connect those with a line. The point, that another way of saying that is you can't have a perfectly vertical line on a velocity graph. It has to have a slight, has to lean slightly. Okay. All right, so that's all well and good. So our goal is to figure out how far it was. So you can do we know that the velocity for the let's break it into phases, phase 1 and phase 2. And the first phase is still the same equation, delta F over delta T, or if you prefer, you can use delta X over delta T for the call the function X. It really doesn't matter. And so how much did the X change? Well, it was velocity times the change in time. Okay? Now, what you're going to do is you're going to add that to the 100. Okay, the final position is not equal to delta X. The final position is equal to 100 plus the increase, plus the change in delta X. Okay, and so let's see, for the first leg we'll have delta X1 equals V1 times the change in time for the first phase. So that's going to be 200 times 5. So 1,000. Okay, so I'm going to go way out here. If I could, if here at 1,100, because that's 1,000 plus 1,100. So X final is the initial value. Let's call that X0 plus the change. So 100 plus 1,000, and that's how I got 1,100. Okay. Very good. So that's where we are. And then what about for the second phase? All right. Well, after the second phase, you simply do the same, something similar. So you've got delta, let's call it delta x2, and that's going to be the new velocity times the new change in time. And that's going to be, it was 100 for 3 hours, so it changed by 300 this time. So the new position, we simply move to the right by 300 on the x-axis. Okay, so I would put there 1,400. Okay, and 1,400 would be where the rocket ends up. Okay, now this is important. You could have done this problem by turning it into a geometry problem. You could have simply found the area underneath all of the purple line, okay? And in order to do that, you could have split it up into 2 rectangles. And we know that the area of a complicated piece is the sum of the areas of the pieces it's made out of. So the first piece, 200 times 5, is 1,000. The other one, 100 times the width is 3, that's 300. Okay, add those together. So the area is 1,300, and that's how much it changed. So you add that to the 100, and that's what gives you 1,400. Okay, so again, the area underneath a slope graph, a velocity graph, has this mysterious connection to the function and what the value is. Okay. Now, for the last thing I'd like to leave you with, so far I've used area in order to find the position. Okay. Now, let's turn it around. Suppose for some reason it was difficult to find the area underneath the velocity graph. Okay, I've given you I've given you a simple velocity graph, but suppose, let me go to a different problem, a different whiteboard. Okay, suppose that your job was to find the area underneath this velocity, this looks like the Manhattan skyline. Okay, and imagine that I had a bazillion different twists and turns, and so let's say it was really hard to get the area. Okay, and maybe it even went below, that's allowed. Okay, so what I am saying is that you could, if for some reason finding the area underneath was too painful, you could simply, if you knew the f function, okay, so let's say this is v of t, okay, and remember that we said that v was equal to the change in f over the change in t. So the area was the sum of all the v delta t's for all the rectangles. Uh, Sum of v delta t for all the rectangles. That's what on the last one I had two rectangles, right? Okay. Now, so however, we also know that that's equal to delta f. Okay. Well, what's delta f? That's the final value of f. Actually, let's do it this way. What's the final value would be f of t final minus f of t initial. Let me just shorten my subscripts. T sub f and then t sub 0. Okay? So if for some reason you knew what the function f was, can you, and let's say you had, your job was to calculate a complicated area under a graph. If you knew what the corresponding f was, could you see that you could simply find this simple difference, and that you could turn an area problem into simply finding a difference. Okay, that is a big deal. Think about how many shapes in geometry have complicated areas. Maybe you remember the formula for the area of a trapezoid, maybe you don't. What about a rhombus, a parallelogram? What about a circle? What about an ellipse, an egg shape? Okay, you can quickly imagine shapes that have hard to calculate areas. Okay, let's imagine that we were able to interpret those as the area under a slope graph or a velocity graph. And then suppose by some strange way we were able to find the corresponding delta f. Can you see that that would be a way to turn a geometry problem into a simple difference? Okay, that's kind of giving you a sense of another thing we're going to be doing in the second semester of this calculus class. That's very cool.